Swinburne Hawthorne's campus has always been shaped by water usually out of sight, under asphalt, trapped in pipes. Today, we imagine a different future, a campus that drinks the rain, cools itself, and welcomes everyone by designs. Swinburne sits inside the Gardiners Creek catchment with the areas of 112 square kilometers. Fit plan has flagged the risk of overland flow paths in the special building overlay mapping. Climate change with sharper, short-duration storm over the same street and pipes, ponding and flash flow concentrate right where people move.
Well, one of the most significant changes to the landscape that comes with urbanisation is impervious cover. We are talking about anything that prevents rain from soaking into the subsurface, buildings, sidewalks, driveways, and parking lots. Impervious cover is a big issue. When it rains, that water has to go somewhere. If it can't soak into the ground, it washes off into creeks and rivers. That means increasing the magnitude of floods and the amount of pollution in waterways. It also means less water goes to recharge groundwater resources. But not all cover has to be impervious. Permeable pavements are designed with materials and structures that let water seep through. Beneath the surface, layers of aggregate temporarily store the water before it slowly infiltrates into the soil. According to the Australian Soil Classification, in Hawthorne, especially in Swinburne University, the soil classification is chromosol. This kind of soil is characterised by a loamy surface layer over a clayey subsoil. This kind of soil has varying infiltration rates depending on its texture and structure, but generally the infiltration is not that good. The real workhorse of a permeable pavement system is the reservoir below. This is generally made from a layer of stones of uniform size to create voids that temporarily store water coming through the surface pavement. This layer of stones temporarily stores the water before it slowly infiltrates into the soil. In addition, creating ponds or rain gardens helps reduce flow rates and increase rain runoff reabsorption by the soil. And finally, implementing water paths will help to manage the flow rates connecting them with the system of ponds.
Using ArcGIS, we adjust the surface absorption parameters to compare the materials. The simulation shows how the permeable concrete would absorb runoff if used to replace the current campus pathway.
Our design is driven by the sponge city philosophy, pioneered by Professor Chien Lin. This shapes our three core goals. First, absorption. Inspired by absorbent pathways in the goods line in Sydney, we'll transform our own pathways from hard concrete into living absorbent corridors. Second, redirection. Like Tanner Springs Park in Portland, United States, we'll create new, man-made creeks, guiding water and cleaning it as it flows. Finally, catchment. Professor Yu's masterpiece, Yunweizhou Park in Jinhua, China, shows how a resilient park can be designed for flooding. Our design uses this logic for water storage and flood prevention. We are creating a campus that actively manages water through absorption, redirection, and catchment.
In Civil 3D, we simulate water flow directions and identify the lowest catchment areas. During an event, runoff moves down John Street, past through Glenferrie Station, track along Wakefield Street, and accumulates at the existing car park, the lowest point on site. Using tide flow in 3DX Max, we model an extreme storm over Swinburne Hawthorne campus. The main flow lines originate on higher terrains around AMDC and ATC and AS buildings, then run downslope toward Glenferrie Station. The simulation highlights likely flood-prone zones at the two car parks, John Street and Wakefield Street, near the garden, where fast runoff concentrate and ponding develops.
With the findings we got from the analysis, we began testing a range of strategies to implement a sponge city concept on campus. designing detention ponds and waterways to detain, redirect, and absorb stormwater. And through simulations, we evaluated and refined these designs to identify the best option. And ultimately, the results showed that option 4 was the most effective solution. In our proposal, we first identified the existing green areas on site and introduced detention ponds and smaller sponge zones with vegetation to enhance water absorption. We then integrated waterways along Wakefield Street and John Street to redirect stormwater while enriching the landscape with water features. And finally, the existing car park and lake lab were removed to create larger catchment areas, reducing the risk of flooding during extreme storm events. The existing rain simulation revealed flooding across multiple areas, while the proposed landscape with added green sponge zones help catch and absorb rainwater, slowing down runoff and reduce flooding risk. These areas allow water to soak naturally into the ground, making the site more resilient during heavy rain. A closer view shows that the sponge areas at the Late Lab and AR building can be seen detaining runoff from higher areas of the site, while the remaining water flows towards the river and detention ponds located at the lower points. In our proposal, the existing Late Lab is demolished and transformed into a detention pond that serves as an open public space during dry periods, while retaining water during heavy rainfall. Along Wakefield Street, a central river is introduced to redirect stormwater while naturally filtering the water through vegetation and gradually releasing the water into the detention ponds. Finally, the existing car park is transformed into an urban wetland park, creating a vibrant public space that not only improves stormwater management but also enhances the campus experience.